Alright guys, geometry class, welcome to some more discussion of area. The topic today is going to be regular polygons, so regular hexagons, pentagons. Take a look at your paper, there might be some other figures on there, octagons, nonagons, decagons, dodecagons. It could be a square or an equilateral triangle, but we're going to stick with regular polygons. So we're going to review what regular means. Again, like we do with the other shapes, we're going to break a regular polygon into triangles to show you where the formula comes from. The first little brainstorm I think is on your paper. Kind of recalls you to remember what area is in your own words and what perimeter is in your own words. So I would write that down in your own words real quick. Pause this thing. I'm not going to give you sentences to copy. Write down what you remember for perimeter and write down what you remember for area. Big concepts that you have to have mastered by the end of this week, really, and the end of this chapter. Hopefully something you came up with is areas on the inside. Perimeters is something around the outside. Usually students come up with that. Area is space, whereas perimeter is distance or length. Area is square units, or number of squares that fit inside a figure. Perimeter is distance or length around the outside. And like I said, put that in your own words. You might also say something about perimeter being the sum or the addition of all the sides. I'm intentionally not giving that to you in a sentence format. Those are the ideas you should have brainstormed, come up with on your own. The formula we're going to come up with today for area of regular polygons, actually the area is in terms of the perimeter. So a perimeter is actually a variable you find to find the area of a regular polygon. So that's why I have that question up there. The raining question on the bottom, what type of polygon-like object could assist you and prevent you from getting rained on? Looks something like that. And you might say, what does that have to do with today? If you look at the top view of that, you have a type of regular polygon. So we're going to talk about how to find the area of a regular polygon. Why did I throw that up there? It's kind of a nice picture. If you look at this umbrella, how many panels does that umbrella have? And if you count those up, you can quickly see it has 8 panels, which means it's actually sort of like an octagon. It looks like they have some curvature down here. So it's not truly an octagon, but it's pretty close. And I just like how the octagon has been broken up into 8 triangles. That's exactly what we're going to do to find the area of, that's what you could do to find the area of any polygon. You could break it up into triangles. You notice all of these triangles meet in the same spot. They all meet at the center of this octagon. So we're going to kind of define what the center of a polygon is as well. So we've got some vocab, kind of sort of front-loading some vocab on your paper. The first one on there, actually I'll give you a second to label the vertices of this pentagon, T, O, D, A, and Y, and try to find point C, which would be, again, at the center of this pentagon, or any polygon that has a center. We'll talk about that in a minute. And I think on your paper I may have drawn a circle here. So for the first time in a while, we're going to relate circles to actually other polygons. And you may see that the center of this polygon also relates to the center of the circle, the same thing on there. So the center of a polygon is actually the center of a circle that's circumscribed about it. Or the polygon is inscribed inside the circle, another way to say that. So, talk about where the polygon center is. It's equidistant from all of its blank. Now, as you try to fill this thing in, you might say, well, this is equidistant from each of the vertices of the polygon. You might also say it's equidistant from the sides. Either one of those words would make sense on here. In terms of the definitions on here, I'm going to talk about this being equidistant from the vertices. In other words, if I draw a line from C to Y, or C to T, or C to O, or C to D, or C to A, those would all be congruent. So draw at least 1 or 2 of those, and preferably just 2 on the bottom maybe. And the reason I'm doing that is because I want to show this little triangle here. Think about, ignore the polygon for a second. What do you call this segment from the center to the edge of a circle? And this is the same thing, from the center to the edge of a circle. What do you call that segment? Hopefully the word radius comes up in your brain on here. That's the second definition. A polygon actually has a radius. We usually think of radius as just being for circles. Polygons also have radii. So a radius of a polygon starts at the center and goes to, and I put this into 2 words here, you could say it's the edge or the outside of the polygon, or the corner of the polygon. So this is the definition in terms of a polygon for radius. That's the definition of the center of a polygon. Two words that we usually use for circles. They also apply to polygons. And some of you may have seen this beautiful creature before. They live in North America. They are only marsupial. You might think I'm crazy even having it up there. There's a reason that I have that animal up here. That animal is called an opossum. Some people call them a possum. They don't pronounce the O, but it's a very soft O sound. The reason I have that animal up here is, again, is an opossum, is so you understand the pronunciation of this word. This is called opossum. It sounds a lot like a possum in terms of the soft pronunciation of the beginning of that word. It's not an apothum or an opothum. It's an opothum. Sort of a soft A sound, kind of like you say opossum. It's sort of a soft O sound on there. It's nice that I'm doing this on my own because no one can argue with me how to pronounce possum, which I always get into that argument with students on here. But, so an opothum of a polygon is an important little distance here. It's the distance, and I'll kind of draw one on here for you, it's the distance from the center of the polygon to the midpoint of one of the sides, or to the edge. And of course, if I say it's going to the midpoint, that means it has to be perpendicular. So I know I can see on your screen, it's probably not showing up very good. There's a right angle box up here, but it should hit at a right angle. That little segment's called an opothum. And you should be able to see the difference between a radius and an opothum, and you have to know that difference, because you'll oftentimes be given the radius, and other times you'll be given the opothum, and those are two different givens, two different approaches to how you solve this. Again, the opothum goes from the center to the side or to the edge of a polygon, and it happens to hit right at the midpoint. Now think about this. The whole point of this is to kind of give you some vocab so we can go and find area. If I told you to find the area of this triangle, ignore everything else on the drawing, just look at this triangle. What do you call the opothum in terms of this triangle? Hopefully you're going, oh, that's the height, that's the altitude. That's one way to find the area of a regular polygon. Find the area of this little triangle and figure out how many of these triangles fit inside here. So that's what we're doing on the next thing on here. The opothum is really like a little altitude for one of these little triangles. So what I'd like you to do, I want to do a couple things here. I give a whole bunch of shapes here. You've got, I think it might say on your paper to name these figures. This has 4 sides, so it's obviously a quadrilateral, or in this case a square. 5 sides, of course, is a pentagon. 6 sides, hexagon. 7 sides, heptagon. 8 sides, of course, is an octagon. Decagon, of course, you remember dec means 10. Dodec means 2 more than dec, so it's 12. And then n-gon, we're going to get to a formula by the end of this. So what I want to do quickly, I want to kind of remind you what regular means. Regular, of course, means all the sides are equal and all the angles are equal. All the angles are congruent, all the sides are congruent. That's what the word regular means. Just a quick little refresher on there. Another vocab kind of refresher. It says find the measure of each central angle. I have not talked to you about what a central angle is. A central angle is this entire angle here. If you remember the opothum we drew a minute ago, this entire thing, the opothum cut that entire angle in half. So we're going to get to use some trig here. It's going to be great. But to use the trig, we're going to have to know these angles. So again, I threw my names and my shapes on here: pentagon, hexagon, octagon, heptagon. What I want you to do is draw some diagonals again. And I can see it didn't come up that well on the page. I need to darken it, I guess. Here's your 2 diagonals. The square is really easy. The central angles are the angles that are at the center. These 4 angles that are at the center. You can tell just by looking at them what they are for a square. For a square, they're obviously 90. They're all 90. Do the same thing for all of these other shapes. Draw in all these little segments here. Of course, if I'm going from the edge, from the vertex to the center, I'm asking you to draw radii. How many radii can you draw for the pentagon? Of course, you should be thinking 5, 1 from each of the vertices. And then figure out the measure of each of these angles. Not with a protractor, just use logic. This is typically a time when I walk around class and I tell people to just do it. Hurry up and do this. And people, sit for a minute, I don't know how to do this. How do you calculate that? And a few people stumble on it, and then when they realize how to find it, it's so obvious. So it slaps you right in the face. So figure out the measure of each of these angles. And I'm going to just throw the number 72. Eventually you'll come up with 72. Do that for all of these. And eventually, if you haven't figured out yet, you'll see where the 72 comes from. You'll see where the 90 comes from. I had a circle up here a few minutes ago. It does relate to something you should maybe remember about a circle. You don't know a lot about circles, but hopefully you remember about circles. Again, do the same thing for a hexagon. Draw in all these radii, which of course means you're drawing 6 radii. I'm sure you can figure out each of these angles. Again, I suggest you pause and work on this. You should eventually get 60 for each of these. Heptagon and the octagon. The octagon, think about how many radii you're drawing. You end up drawing 8 radii. Heptagon, I'm only going to draw 2 of them on here, but you should have 7 radii. And this is the only one that I think that ends up being a decimal value on here. You should have 51.4 for that central angle here. And again, I could label any of these angles as 72, or any of these as 60, or any of these as 90. I don't have all the other triangles. Any of these is 51.4 approximately. I believe the octagon, it ends up being, I think, 45 degrees. Now, if you haven't figured out where that's coming from, it's coming directly from the radii. It's actually coming directly from this prefix, penta, hex, hept, oct. So if you haven't figured that out, maybe discuss with somebody next to you. This is a time I love to hear people discuss and compare ideas. What do I do with penta? What do I do with 5 to get 72? What do I do with hex? What do I do with 6 to get 60? What do I do with 7 to get 51.4? What do I do with 8 to get 45? And it might be obvious to some of you by now. Sorry if I'm drawing it out too long. This, of course, these 4 angles add up to 360. These 5 angles in the center add up to 360. These add up to 360. These that aren't here would add up to 360. These add up to 360. So it's basically 360 divided by the number of radii, or in this case, the number of sides. So for a decagon, if it has 10 sides, you probably know it's going to have 36-degree central angles. You don't have to draw these on here. It's just knowing that if it has 10 sides, 360 divided by 10, each of these little angles would be 36. What if I added more sides? If it had 12 sides, you'll see this number is progressively going down because there's more and more of these triangles. 36, when I get to 12 sides, should have 30 degrees. Again, it's 360 divided by 12 in that case. And for the n-gon, this is again getting to actual formula. Like we said, it's 360 divided by whatever this prefix is, penta, hexa, if it's 6 or 5, or n in this case, the number of sides. This is the formula for finding a central angle. You're not going to need this a lot, because a lot of you are just going to go, oh, I know a pentagon's 72, I know a hexagon's 60. These numbers kind of just need to be fresh in your head. You will get stuck on problems if you don't know these. So maybe have this part of the notes handy, and you can go back and find it, because we're going to start doing trig. And when you do trig, as you know, you often want to know the angles to find the sides. That's what we're going to have here. So here's the other big part of your notes, is the actual formula. The area of any regular polygon, I think there's a box for that on your paper, is equal to and there it is right there, area is equal to 1/2 times a, little a, times capital P. And yes, it matters whether they're lowercase and capital. They mean something different. As all of you know, capital A stands for area. Capital P, as you know from the beginning of these notes, look at the top of the beginning of your notes, capital P stands for perimeter. We talked about perimeter in the beginning. Little a is a new one. Little a is that new little a word you just came up with a few minutes ago, apothegm. So this, in terms of a sentence, this equation is the area is equal to 1/2 times the apothegm, little a, times capital P times the perimeter. So on your paper, and I just jumped up here a second ago, you've got a hexagon here. Take that hexagon and cut it up into 6 triangles. 1, 2, 3, 4, 5, 6, and we're going to focus on this one. Now that's the formula. That's the formula you're using for all your homework. Because it's a formula, it's a theorem basically, we're going to prove it. And I've sort of given a sketch. I think it's a 1, 2, 3, I think it's a 5-step proof on your paper. I've kind of given you some questions. These are kind of like the reasoning behind it, but there's sort of some questions on there we're going to go through. I'm just going to pause for a moment here.